good enough. It's done, right? Okay. So, hi everyone. Welcome to a new session of our geometry seminar. So, it's a pleasure to introduce to Oliver Goertsches, who will talk about on the GKM correspondence in dimension 6. Thank you, Oliver.
Yeah, thanks a lot for inviting me. Happy to give this talk. Yes, so this is about the GKM correspondence. Most of the things I will say will take place in dimension 6. I will explain later why this is so. So throughout the talk, I will be interested in actions of compact tori. So T will always be the compact Lie group, which is given by a product of finitely many circles, and I will let it act on some compact smooth manifold. So I'm also interested in geometric structures on these manifolds, like symplectic structures, Kähler structures, or other stuff, which is left invariant by this action. But and some symplectic and Kähler things will appear in the talk, but most of the time I will focus just on the smooth manifold itself and just some smooth action on this. Right? And so the point of view I want to take is that so the larger the dimension of the torus is with respect to the dimension of the manifold, in some sense, the more rigid the action is, right? So if I'm, so to say, in some extreme case, like the following. So if I assume that my action has fixed points, right? So m superscript t here is the set of fixed points. So the set of points in the manifold whose isotropy group is just equal to the whole torus. And if this is non-empty, so if the action has fixed points, and in some sense the dimension of the torus is very large, meaning it is half the dimension of the manifold, then the action is completely determined by the orbit space of the action and the occurring isotropy groups, roughly. So this is a rather rough statement. I will make it a little bit more precise later. Yeah, so this is supposed to say, so if my torus is very large, half the dimension of the manifold, then it is very rigid. So let's give some very easy examples. Here, the very basic example is just I look at a circle acting on the two sphere by rotation around some axis, right? Then I have two fixed points, right? If I rotate like this, the north and south pole are fixed, and all the other orbits are just circles. Then my orbit space is just yes, the orbits are parameterized by the height function, by the height, and the orbit space is just homomorphic to a closed interval. Right? So 0 and 1 correspond to the two fixed points, and the rest of the orbits are free. Right, and so this rigidity up there that I mentioned is just the statement that if I have any circle action with this orbit space, which has these two fixed points and the rest of the orbits free, then I'm already in the situation that I have the circle acting on the two sphere. This is the only example with this property. Okay, so let's go up dimension a little bit. Also, let's look at the two torus acting on CP2 here. Standard action, I look at, so I take these unit complex numbers here, T2 and T1, so, right? So they are in my two torus, and I let them act on homogeneous coordinates here, on points in CP2 given in homogeneous coordinates, just by multiplication in two of the coordinates. Then the orbit space is a triangle, right? And the, so say the dimension of the faces of these triangles corresponds to the dimension of the orbits, right? So we have three fixed points here of these actions, which are just given by 1, 0, 0, 0, 1, 0, and 0, 0, 1, and they correspond to the vertices of the triangle. The edges correspond to one-dimensional orbits, and in the interior we have two-dimensional orbits, right? And again, conversely, if I start with any T2, if I have any T2 action on some four-dimensional manifold whose orbit space is a triangle and whose isotropy groups are as given here, then this is already T2 acting on CP2. Okay. So I don't see your videos. So if there are any questions, then just ask them at any point, or make some other noises maybe from time to time if everything's clear.
Okay.
Okay. So just interrupt me if anything is unclear. Okay. So let me speak about the classes of actions that I will not be interested in today, right? So this is well-known theories that are more or less perfectly understood from my point of view. But let me mention them in order to mention the extreme cases which I will not speak about today. So this is quasitoric manifolds. They are by definition manifolds with actions of the following type. Again, I assume that my acting torus has half the dimension of the manifold. I assume that my orbit space is a simple polytope, right? As in the examples before, right? I had an interval, closed interval, this is a polytope, and a triangle is also a simple polytope. And moreover, one assumes in this theory that the action is locally standard. So this definition will not play any role later on. This just means that locally, the action looks like some open subset of the standard Tn action on C to the n. In particular, this implies that all the isotropy groups are connected. Right? But not so important. Some technical assumption here. And then the statement is that such manifolds are determined by this orbit space, which is a polytope, and the isotropy data. Right? Okay. And as a special case of this, maybe this is more well known, one has toric symplectic manifolds, right? Any toric symplectic manifolds is quasi-toric. And so for those of you who know toric symplectic manifolds or Hamiltonian actions on symplectic manifolds, then you know that the orbit space of such a toric symplectic manifold is, it is quasitoric, so this is a simple polytope, and it is also isomorphic to the momentum polytope, which by definition is a polytope in the dual of the Lie algebra of the torus that is acting. And also here we have this is the famous Delson correspondence. This polytope in T star, this Delson polytope, determines the manifold up to equivariant symplectomorphism. Right? So in all these toric settings, so toric manifolds and its generalization, the situation is like this. You have a group action, the torus is very big, and you can associate to this action some combinatorial object, right? In this case, it's a polytope with some additional data. You have a polytope, and you label this polytope or its edges, its vertices, its higher dimensional faces with the corresponding isotropy groups, and this then determines the whole space. Okay, so this is all well known. Now I want to speak about GKM theory. This GKM theory, this is named after a paper by Goertsches, Kottwitz, and McPherson. So in this theory, one relaxes the assumption on the torus, or on the action, meaning that the torus is no longer assumed to have such a high dimension. It can be of arbitrary dimension. So as an effect, one can no longer associate a polytope to it, but one relaxes the assumptions in just the right amount, so that one can still associate a combinatorial object to it, but which will not be a polytope anymore, but which will be a graph, right? And then one asks, what can one still do with this graph instead of the polytope in the standard theory? Okay, so before we had the fixed point set, right? This was M superscript T. This was the zero-dimensional orbits. Now we also look at the one-dimensional orbits, right? So M1 will be the set of points whose orbits have dimension 0 or 1. And this is we call the one skeleton of the action. Okay, so let's look at the two examples from before. If I have just a circle acting, then of course the one skeleton is everything, right? So everything is, every point has an orbit of dimension at most 1. If I look at the other example here, T2 acting on CP2, then my orbit, a point in here has orbit dimension at most 1, if and only if at least one of the coordinates here is 0. And this corresponds precisely to the boundary of this of the polytope in the orbit space. In the manifold itself, we have a union of 3 two-dimensional spheres of 3 CP1s here, right? So the 3 CP1s corresponding to each of the 3 coordinates being allowed to be 0. Right, so I have 3 CP1s which are sort of glued together, in a as a circle of 3 spheres. Right, and if I pass to the quotient, every one of these 2 spheres becomes a line, right, and they form the boundary of the triangle in the orbit space. Okay, hope that was understandable. Yeah. Okay, so this is now the definition of a GKM action. So I look at again, tori acting on compact, orientable, smooth manifolds. I have this overall topological assumption here that the odd cohomology of the manifold vanishes. Usually, no, it's not true. Sometimes one considers integer coefficients. Sometimes one considers rational or real coefficients. In this talk, I want to assume integer odd cohomology vanishing. Right? Okay, so I have this global topological assumption, and then furthermore, just assumptions on the on this one skeleton that I just introduced. Right. So I assume that I have only finitely many fixed points, and I assume that the one skeleton has exactly the structure as in the examples before. Namely, I assume that the orbit space of my one skeleton is a graph, right? Or in other words, if I want to look at the one skeleton, not the orbit space, but inside the manifold, then I just assume that the one skeleton is the union of 2 spheres, right? As was the case before. Okay. So these 2 spheres are so they are automatically fixed by a codimension 1 subtorus. This is automatic because there is no effective 2 torus acting on a 2 sphere. Okay, so of course my quasitoric manifolds from before, they satisfy these conditions, right? So the one skeleton of the action is just everything in the manifold which lies over the vertices and the edges of my orbit space. Right? So the orbit space is a polytope, and then I take everything above the vertices and the edges. But there's also many more examples that satisfy this. For example, I can look at homogeneous spaces. If they have equal rank, then I can look at a maximal torus inside the isotropic group and let it act by left multiplication. And this is a nice class of examples of GKM actions, which was considered by Guillemin, Holm, and Zara.
Oliver,
Yes?
please. One question: these homogeneous spaces satisfy the condition on the cohomology?
Yes, so this is in fact equivalent for homogeneous spaces. So this is compact Lie groups, right? So if I have compact Lie groups G with the closed subgroup H, then the quotient has vanishing odd cohomology if and only if the ranks are equal.
Okay.
Maybe I need, so this is for sure true with rational coefficients. Okay, so for integer coefficients, I need some more, sorry. So so with rational coefficients, this is true. Right? So the definition of GKM is sometimes with integers, sometimes with rational coefficients. So for rational, this is
Okay.
true. Yes. Okay. So as I said, so when I have a GKM action, then we still want to associate a combinatorial object here. And it almost just appeared. Namely, we already have a graph, right? By definition, the orbit space of the one skeleton is a graph. right? So again, so this graph has vertices and edges. The vertices are the fixed points, and what do I do for every invariant two-sphere in the one skeleton? I draw an edge between the two vertices that contain this two-sphere, right? So two-sphere torus acting on this effectively, then I always have exactly two fixed points, and yeah, so I can draw a line between precisely these two fixed points. Okay, and then I do something similar as in the quasitoric setting. So there I look at the polytope and I label the faces with the isotropy groups. I do the same here, right? So if I have an edge, then I label it with a weight, right? And I can look at this from 2 points of view. So I have a torus acting on this two-sphere. This has a codimension 1 kernel, right? A codimension 1 subgroup acting trivially, and this defines a homomorphism from the torus to the circle, and I take its differential, right? So this is then a linear form on the Lie algebra of the acting torus modulo plus minus 1. Put differently, one can also look at it like this. So you look at one of the two fixed points in this sphere. You look at the isotropy representation. This decomposes into irreducible submodules. Each irreducible submodule corresponds to one of the spheres, and I look at the weight of this irreducible submodule. Right? So if I have some more geometric structure, for example, an invariant almost complex structure, then I can also define weights, not modulo sign, but as honest linear forms, because I can make sense of clockwise and counterclockwise rotation. But in general, I only have this modulo plus minus 1 here. Okay, so this is called the GKM graph of the action. It's an n-valent graph if my manifold is 2 n-dimensional. And yeah, of course, so far our main example is this. So if I have a quasitoric manifold, then the GKM graph just consists of the vertices and edges of the orbit space considered as a polytope. Okay. Okay. Okay, so this is the definition. I want to give some applications of this theory. To start with this theorem that maybe explains why I like this theory. So my statement is that this theory is rather powerful in low dimensions, and with low dimensions I mean dimension 6. Why do I mean dimension 6? Because this is the first dimension in which really something GKM can happen. Because below dimension 6 we only have the toric setting, right? In dimension 2 we only, I mean, there's almost nothing. In dimension 4 we have either circle actions or two-dimensional tori acting with fixed points. If I have circles acting, then the one skeleton is everything, right? So this cannot be GKM in 4 dimensions. So I have to have a two-dimensional torus acting, but this is then already quasitoric or something similar, right? So this is not really a GKM situation. So what I should look at as the lowest possible dimension is dimension 6. Right? Okay, and here we observed this here, namely, if I have a simply connected closed 6-dimensional manifold with this topological assumption here, which is equipped with a GKM action and with connected isotropy groups, then I claim that this combinatorial object, this graph, determines the diffumorphism type of M. Right? Yes, so compare this to the statements from before when you have like quasitoric manifolds. They are determined by their orbit space, by this combinatorial object, up to equivariant isomorphism. Here I have something a little bit less. I only have a non-equivariant diffeomorphism. Later I will also speak a bit about whether one can improve this to some equivariant isomorphism. But here it's only a non-equivariant statement. So I will give some example, but let me give a very, very rough sketch of the proof. So the GKM graph encodes. So this is what Goertjes, Kottwitz, and McPherson originally did in their paper. They did equivariant cohomology, right? And from this point of view, GKM theory is interesting because the GKM graph encodes the whole equivariant cohomology ring of the action. And it encodes more. It also encodes the equivariant characteristic classes. Right? So this was known over the rationals with the characteristic classes. We had to work a little bit more here with these characteristic classes with integer coefficients. But so roughly these. So the basic statement that cohomology ring and characteristic classes are encoded in the GKM graph, this was known. Right? And then we just had to combine this statement that all this topological data is encoded in the graph with the diffeomorphism classification of six-dimensional simply connected closed manifolds by Wall, Yupp, and Zuber. Right? So they claimed that so in this situation up here, odd cohomology vanishing, we only need the ordinary cohomology ring and the first Pontryagin and the second Stiefel-Whitney class to determine the manifold up to diffeomorphism. Roughly, this is the case because so very rough. So they use surgery for this theorem. Roughly, this is the case because in dimension 6 there are no exotic spheres. So this is why this works here in dimension 6. Okay, so let's apply this to an example. This is Eschenburg's twisted flag manifold. So this is an example of a biquotient. So I like to make advertisements for biquotients whenever I can. So if you do geometry, you should look at biquotients at least once in your life. So I look at the following action. So again, we have the two torus acting, but this time I let it act on the Lie group SU3. And I do something a little bit different than letting it just act by left multiplication or right multiplication. I let it act on SU3 in this strange way here, right? So S and T are, again, unit complex numbers. And I look at these two matrices here, which are not in SU3, but which are in U3. And I sort of say conjugate with the matrix G in SU3 with these two matrices. And I land again in SU3 because the determinant of this left matrix here is the same as the determinant of the matrix here on the right. Okay, so now believe me that this action is free, so we can look at the quotient space. Right, this is usually denoted here by this double slash in order to distinguish it from the ordinary flag manifold SU3 mod T2. Okay, so this is one of the most interesting examples of a biquotient. This was introduced by Eschenburg in his habilitation thesis. So biquotients were mostly they are being considered in Riemannian geometry because Eschenburg in his habilitation thesis he looked at biquotients and asked which of them admit a metric of positive sectional curvature. Right? And this is one of the so this is the only even dimensional example which does, right? So this is very important from the point of view of positive curvature. Okay, but I claim that these spaces are also interesting from other points of view in other geometries. Okay, so this is Eschenburg's flag manifold. It is somehow a little bit similar. The definition is a little bit similar than the definition of the ordinary flag manifold, but it's really a different manifold. For example, the cohomology groups are isomorphic, but the cohomology ring of these two spaces is not isomorphic. Okay, so it's really a different manifold. Okay, and on this manifold here on SU3 mod T2, it is a twisted flag manifold, we still have some action, we have a little bit less symmetry than in this homogeneous setting, right? If you look at SU3 mod T2, and T2 is acting just here from the right, then you still have the whole SU3 action from the left by left multiplication, right? So homogeneous space. So, but here you quotient in a more complicated way. So you cannot let SU3 act by left or right multiplication act here in a well-defined way. But what you can still do is you can look at the maximal torus of SU3, so the diagonal matrices, and let it act on this quotient by left multiplication, because these diagonal matrices, they commute with this matrix here on the left. Right? So this gives a well-defined action. So I have a two torus action on this six-dimensional manifold left. Okay. Okay, so here it is again. So manifold, I have the T2 action by left multiplication. I do not have a T3 action, right? I have a T2 action. So this is not quasitoric or anything, but it is one. The torus is one-dimensional less, and I claim that this action is an example of a GKM action. Right? So we'll not compute this here, but you can believe me that it does. This is what the GKM graph looks like, right? So this has 6 fixed points, and these edges correspond to the two spheres that connect these two these fixed points. Okay. Okay. So when so this is the picture. Now forget about this flag manifold for a second. There is another so this is another paper from the end of the 90s by Susan Tallman. In this paper, she constructs the first Hamiltonian torus actions. So this is you can write T here, not T2. So the first Hamiltonian torus actions on compact symplectic manifolds with isolated fixed points, which do not admit an invariant Kähler structure. Right? So if you recall toric symplectic geometry, right? If you have the half-dimensional tori acting, then classical theory says that you always have an invariant compatible Kähler structure, right? Toric symplectic manifolds are always Kähler, but this shows that if you drop the dimension by one, dimension of the torus by one, and you still assume that you have isolated fixed points only, then this is no longer true. And how did she come up with her example of such a symplectic manifold? She present a slight modification due to Woodward. This goes like this. You start with two manifolds, six-dimensional, which are symplectic but have an invariant Kähler structure, right? So these pictures here are now to be understood as the momentum images of these as the images of the momentum maps of these examples, right? So this example here, for example, you can choose as the standard flag SU3 mod T2, right? So you take two appropriately chosen invariant Kähler manifolds, and you glue them in a symplectic way. So this is what these dotted lines here are supposed to symbolize. You cut this here and you cut this here, meaning you take the pre-image under the momentum map of the left half here and of the right, the upper half here, and you glue them together and you obtain this picture. Right? And what she did was to show that this works in a invariant symplectic way. So what she obtains is a symplectic manifold with exactly this momentum image here. And then what she showed is that any symplectic manifold with Hamiltonian action with this momentum image cannot admit an invariant Kähler structure. Right? So very roughly, why is this the case? If you sit down in a fixed point here and you follow two edges here, right, and you cut this part of the image, right, then you end up here in some part of the momentum image which is not a fixed point, right? So this is right. So it's not a sub polytope, right? If you in some sense. So this contradicts some criterion of Atiyah, namely. So what you could do if this was invariant Kähler, you could complexify the action, and you would have an action of the complexified torus, and then you can look at torus at closures of the action of the complexified torus, and this would be four-dimensional symplectic manifolds, and their existence would contradict this shape of the momentum image, right? Very roughly. Okay, but this now here by accident is the same image as the image we had before, right? So this action here is GKM, has the same GKM graph as our Eschenburg flag. So we could conclude with our non-equivariant diffeomorphism classification that this example here is diffeomorphic to the Eschenburg flag, right? And in this way, we could solve a question that Tallman asked, namely, she showed that this example did not have any invariant Kähler structure, but she asks if it has any Kähler structure. And this we could answer in the affirmative by this classification, because it was known that the Eschenburg flag admits some Kähler structure. So this is a Kähler manifold whose symplectic form, with a symplectic form that admits some Hamiltonian torus action, but the Kähler form itself does not. But this action does not leave invariant the Kähler structure. Okay, so this is one example of GKM theory in dimension 6. Are there any questions on that?
No.
No? Understandable? I don't know if I'm too fast or too slow or
Okay.
understandable.
No,
it's okay. Okay. Okay, so I want to say a little bit more about whether one can leave out this word non-equivariant in the theorem before. Right? So this goes then more in the direction of the GKM correspondence in the title. So again, we have bijections, right? So toric symplectic manifolds are the same as Delson polytopes when you mod out by the appropriate equivalence relations on left and right hand side. Quasitoric manifolds correspond to simple polytopes with isotropy data. And I want something, so the aim would be to have something similar, like you have GKM manifolds and you associate to them their graph, right? The GKM graph, and maybe this gives some bijective correspondence under some assumptions. Okay, so we can ask about injectivity, right, and surjectivity separately. So let's what we just saw is that in dimension 6, so we have a simply connected manifold, the GKM graph encodes the diffeomorphism type. So this is some sort of injectivity here. And I will say a little bit about the fact that in this dimension, it even encodes the equivariant homeomorphism type. Right? We do not know about the equivariant diffeomorphism type, but it does encode something equivariant, namely the equivariant homeomorphism type. We also know, this is something I do not want to speak about today, that in higher dimensions, all of this does not work anymore. Together with the same co-authors, so we found an example of two 8-dimensional GKM manifolds with the same GKM graph, but the manifolds that are acted on are not even homotopy equivalent. Right? Yes, so still in higher dimensions, GKM theory can be useful because this graph encodes a lot of information, right? Before I said it encodes cohomology ring, the equivariant cohomology ring, all the characteristic classes, they are all in there, but it does not encode the really the homotopy type of the manifold anymore. So this is where its power ends. Okay, and in the surjectivity question asked, if I have a GKM graph, an abstract one, I did not explain yet what this is. I will do on the next slide. If I have an abstract GKM graph, is this realized by a GKM manifold, right? So can I use this theory to give interesting examples of manifolds just by writing down some graphs, right? Like, for example, one often does this in toric symplectic geometry. Like I draw a Delson polytope and consider the corresponding symplectic manifold. This is something, standard tool that one does there, right? So can I do the same thing here? And I will explain that again in dimension 6. This is okay. We understood which are the criteria such a graph needs to satisfy in order to be realized by a GKM action. So this is understood in dimension 6. In higher dimensions, this is still open. This is not clear which graphs are realized by GKM manifolds. Okay. Okay, so to make sense of this correspondence here, I should define what an abstract GKM graph is. Right? So remember, the GKM graph was just, I have this action, I take the orbit space of the one skeleton and I label it with the weights of the isotropy representation. Now I want to forget that these things come from a manifold. I want to define these abstract graphs. Right? So this is a definition that goes back to Gilman and Zara. I just take an n-valent connected graph and with a labeling. And this labeling is supposed to model my isotropy weights, right? So E of gamma is the set of edges, and every edge is sent to some vector modulo plus minus 1. Right? So I did not yet fix a torus, so I do not have a Lie algebra of the torus available, but this will then later become the integer lattice in the dual of the Lie algebra of the acting torus. Okay, and so what do I want? I want to encode the GKM condition. The GKM condition said that my one skeleton is two-dimensional, consists of a finite union of two spheres. Put differently, this means that if I have two weights of my isotropy representations, then they cannot be linearly dependent, right? Because if I had two weights and they were linearly independent, they would have a common kernel, right? And the corresponding fixed point manifold would be at least four-dimensional and contained in the one skeleton. This is not the case, right? So for a GKM action, all these weights of my two spheres, they are pairwise linearly independent. Right? So this is the condition here that I put on my axial function for every vertex of my graph and any two distinct edges here. My labelings are supposed to be linearly independent. Okay, and I have one more condition. I assume the existence of a compatible connection. So connection here is really meant. So is the definition. This notion is motivated by Riemannian geometry, by parallel transport, right? So what do I do here? I fix a method to slide edges along other edges, right? So in this picture here, I start at this vertex. I have the edge E here, and I have the edge F here. And then I can slide this edge to another edge here, which has this congruence relation here. So the weight of my edge on the other side here is supposed to be plus minus the weight here, plus some constant times the edge here. Okay, so this looks a bit unmotivated at first. Where does this come from? So if I fix my edge here, so fix this edge, this corresponds to a two-sphere in my manifold, if the graph came from a manifold, then I can look at the tangent bundle of the manifold restricted to this two-sphere. Okay, So this tangent bundle decomposes into the tangent bundle of the two-sphere itself and the normal bundle. Right? And on the normal bundle, we still have the torus action, right? So the two-sphere here is invariant, then the normal bundle is also invariant. And then one can show that one can decompose this normal bundle into two-dimensional invariant subbundles for any GKM action. And this is precisely the condition that arises when I take an invariant subbundle and I follow the fiber if I follow the fiber of one of the irreducible subbundles all the way until the other fixed point of the two-sphere, then the isotropy on the other side will satisfy precisely this condition here. Okay. Okay. So this, I mean, I will not make explicit use of this condition later on, right? So just, yeah, but it's part of this definition. Okay, so this is an abstract GKM graph. So now I have my GKM correspondence, right? I can send my GKM manifold to this abstract GKM graph. Okay. Yes, I want to explain a little bit. So I want to get to the necessary conditions. When is a GKM graph realizable? And for this, I need to speak a little bit about equivariant cohomology. So equivariant cohomology is a cohomology not of spaces, but of actions, and it's defined like this. Right? So I have this torus. Then I have the classifying bundle, right? ET over BT, right? ET is a contractible space on which T acts freely, and BT is the quotient modulo T, right? So this is a product of CP infinities, as many as the rank of this torus here. And then what does one do in equivariant cohomology? What you do is you replace M by this product here, M times ET, and you look at the diagonal action of the torus, right? What did you achieve in this way? Because ET is contractible, M times ET is just homotopy equivalent to M. Okay. So you replaced M by a homotopy equivalent space, and you replace the action by a free action because T acts freely on ET. Right? So the intuition somehow is that if you have a free action, then the cohomology of the quotient is again a nice the quotient is again a nice space, so the cohomology is a reasonable invariant. So what do? You make your action free and then look at the quotient. The disadvantage is that the thing you get is an infinite dimensional space, so the cohomology is much larger than ordinary cohomology, but yeah, it still has nice features. Okay, so this is an H star BT algebra. So this is a polynomial ring, right? So this is a polynomial ring with as many generators as the rank of the torus, right? So this is an algebra over polynomial ring. How does it become an algebra? You just project onto the second factor here, right? Onto ET mod T. Then the induced map in cohomology gives this algebra structure. Okay, let's look at the easiest example, which is just the trivial action, right? So one should imagine the trivial action gives a trivial cohomology, but that's not true, right? So if you have the torus acting just on a point, then the equivariant cohomology of the point is just the cohomology of the classifying space, which is a polynomial ring in as many variables as the rank of T. Right? So the idea is equivariant cohomology sees the isotropy group of the action in some way, right? So the space here is trivial, but the isotropy group is very large, and this is why the equivariant cohomology of this action is very large. Okay, so there's one important map in equivariant cohomology, which is the map induced by the inclusion of the fixed point set. Right? The fixed point set of the action sits inside M, so you can look at the induced map from the equivalent cohomology of M into the equivalent cohomology of the fixed point set. And here, this is the same as in this example here. It's not a point anymore, but still it is some manifold on which the torus acts trivially. So, and when the torus acts trivially, this product here with this diagonal quotient becomes just an honest product. So by Kühnert formula, you get a tensor product here, right? So this becomes a free module over H star BT. Right? Yeah, just this tensor product. And now there's some strange thing happening in equivariant cohomology, which never happens in ordinary cohomology, right? Here I have a smaller dimensional submanifold embedded into M. Then, of course, in ordinary cohomology, it never happens that the induced map in cohomology is injective, right? If M is orientable, then we have a volume form here, and the volume form restricts to 0 here because this is of smaller dimension, right? But in equivariant cohomology, it happens rather often that this map here is injective. This is very strange. And yeah, so one of the main features why equivariant cohomology is often computable. With this map, you can often embed this equivariant cohomology in this rather easy thing here, right? For example, if my fixed point set is finite, then this is just here the cohomology of a finite set of points, tensor sum cohomology rings, right? And this is exactly what one does in GKM theory. So I assume that my fixed point set is finite. Then I have again this map, right? This is just a direct sum of finitely many copies of polynomial rings, right? So wrote here symmetric algebra of the dual of the Lie algebra that is acting. Okay, so an element in here is just a tuple of polynomials. I attach to every fixed point one polynomial. Okay. For a GKM action, this map is injective, right? So this follows from this standing assumption that the odd cohomology vanishes. Odd cohomology vanishing implies that this map is injective here. Okay, and then, so this is done in this paper by Goertsches, Goertschis, and McPherson. They computed the image of this map. So this, they relied on some paper by Shang and Shelbrett, which already related the equivariant cohomology of M to that of the one skeleton. And then essentially all they had to do is compute the equivariant cohomology of the one skeleton. But in this GKM setting, the one skeleton is just this union of two spheres. So essentially, this is just a Majorvi-Torres sequence. What they have to do here, right? So the outcome is that the image of this map can be written down completely in terms of the GKM graph. Okay, so now, yeah, so the result is this. So here we have f of p. So what is this notation? So p runs over the fixed points, so a finite index set, and f of p for every p is a polynomial, right? A polynomial on this vector space T, right? Polynomial in several variables. And so we have tuples of these polynomials, and the only relation that I have is that so if I have two polynomials attached to, so I have my fixed points, I attach one polynomial to each of my fixed points, and then I have one congruence relation, namely if two of my fixed points are connected by an edge in my GKM graph, this edge has label alpha, right? Alpha is a linear form on T, is also an element E here. Then I ask that this difference here is divisible by this linear form, right? This is the only side condition that I have here. So this computes explicitly the equivariant cohomology as an algebra over the polynomial ring in terms of the GKM graph. Okay. Okay. And now, what did Gilman and Zara do? Remember, they defined an abstract GKM graph. They used this as a definition of equivariant graph cohomology, right? Because you can write this down just for a graph, for a GKM graph. And this is by definition this H star T of gamma. Okay, then another thing, you're maybe not interested in equivariant cohomology, but one of the main features of equivariant cohomology is that often it determines the ordinary cohomology. For example, it does so for GKM actions. It does so with this small formula. If you know the equivariant cohomology, then remember we had this map from H star BT into equivariant cohomology. You look only at elements with positive degree, right? You forget about H0. And then you look at the ideal generated by this here. Okay. And then the ordinary cohomology is just this quotient. Right, so there's a surjection from equivariant cohomology to ordinary cohomology, and one understands precisely what the kernel is. Right? And again, so this thing here, this equivariant cohomology, the algebra structure is completely encoded in here. It's just given by component-wise multiplication of polynomials. So also this quotient here is encoded in the GKM graph. So one can recover the ordinary cohomology of a GKM manifold from the GKM graph. Okay, so now we restrict again to dimension 6, and we ask if the diffumorphism classification from before can be improved. We note that there are two necessary conditions on my graph that it needs to satisfy, otherwise it cannot be realized, because my equivariant cohomology is always a free module. This is, again, something that follows from this assumption that the odd cohomology vanishes. And because my manifold is assumed to be orientable, my cohomology satisfies Poincare duality. Okay, so what we showed is that these two assumptions here, they are in fact sufficient for a GKM graph to be realized by a manifold. Okay, so what we can show is that we have a one-to-one correspondence. Again, have in mind the correspondences for toric and quasitoric manifolds. We have some type of smooth actions. So we have a result where we don't need to assume connected stabilizers, but for simplicity, I restrict to this here. So we take six-dimensional simply connected T2 GKM manifolds with connected stabilizers. And I claim that they are uniquely determined by their GKM graphs. And that conversely, if I have a GKM graph, sorry, if I have a GKM graph with the appropriate necessary conditions, then I can realize them by a GKM manifold. Right, so what are the conditions here? I have to assume that the graph satisfies Poincare duality, meaning that if I reconstruct my cohomology from the graph in the way I did before, then this cohomology has to satisfy Poincare duality. And moreover, the equivariant cohomology of the graph has to be a free module. So these are purely conditions that can be read off from the graph. And then disconnected stabilizers here, they correspond to conditions on the weights. Yeah, so if I have two adjacent weights at the same fixed points, then they have to form a basis of the integer lattice. This is precisely this condition of connected stabilizers. And then we have a one-to-one correspondence here, where on the left-hand side, we consider this up to equivariant homeomorphism, and on the right-hand side, up to isomorphisms of GKM graphs. Okay. Okay, so yeah, so why do I like this theorem? I like this theorem because so it gives the combinatorial descriptions of a class of actions where the acting torus is not of half the dimension of the manifold, right? So this is, it looks a bit more complicated than in the toric setting, but yeah, this is to be expected if the torus is smaller than half the dimension. Okay, I think I have maybe in 3 minutes I can give a very, very rough sketch of the proof. So surjectivity roughly goes like this. So the GKM graph determines the one skeleton of the action. Right? We have this. So we have this graph. We just replace every edge by a two-sphere, and how the torus acts on it is determined by the labeled. So we have the one skeleton of the action. Then we can thicken this a little bit. We can make this 6-dimensional. This was already done in the almost complex setting by Gilliman and Zara. So this roughly already existed. Then we have an open manifold, or a manifold with boundary, if you want. And then we have to carefully attach equivariant handles. Right? So we attach manifolds of the form d4 times t2 in a careful way, which is described by the GKM graph. If I do this appropriately, I get a T2 manifold whose orbit space is S2 times D2. And then I cap this off with S3 times S1 times S2 in order to obtain an orbit space S4. Right? So there are results by Eisenberg and Masuda that say that my orbit space necessarily has to be S4. So I have to construct this manifold in such a way that my orbit space is S4. Okay. And then one has to prove that the odd cohomology vanishes. And injectivity goes like this. So this result by Eisenberg-Masuda tells us what the orbit space is. My GKM graph is an orbit space. So it lives in this orbit space S4 here. If I have two examples now of GKM manifolds, they have the same orbit space as 4. They have the same GKM graph in there. So I can fix a homeomorphism of these orbit spaces, which intertwine these GKM graphs, right? Why does this work? This works because dimension 1 is low enough in dimension 4 that there are no knotting phenomena happening here, right? There's no knot theory for curves in S4, right? And then I have to lift this homeomorphism equivariantly in a careful way. Okay. So why does this not work in for equivariant diffeomorphism? This is because the orbit space is 4-dimensional, right? And as you know, 4-dimensional differential topology is very complicated, right? So it is not known if there is an exotic smooth structure on S4, for example, and so we cannot improve this to diffeomorphism. Okay, that's what I wanted to say. Thanks a lot. Okay, so now I see you again. So
Okay. So, are there any questions? Oliver,
yes.
Is there a classification of GKM graphs for dimension 6?
No, there's no classification of GKM graphs in dimension 6. I think there was if I remember correctly, there is some PhD thesis which classifies GKM graphs in dimension 6 with at most 6 vertices, I think. And this is like 80 pages or something, the PhD thesis. So this is already a lot. What we did, we classified GKM graphs in dimension 6, which fiber over n-gons, right? So there is a notion of GKM fibration. I mean, you can sort of guess what this means, right? So you have a so in this case you have an n-gon, right, in the bottom, and you have right? This three-valent graph that maps to the n-gon. You're allowed to collapse some edges, right? But so, for example, let me. So this this Eschenburg flag here is an example of this, right? So this here fibers over the triangle, right? So you if you collapse all the diagonal edges, this here, and this here, then you have a triangle, right? So this this is a GKM fiber bundle over a triangle with fiber a line, right? And we showed, so we classified them and showed that they can often be realized by CP1 fibrations over quasitoric manifolds in dimension 4. But yeah, that's all that's known.
And there is no upper bound on the number of vertices of stuff?
No, there's no upper bound of the number of vertices. So the number of vertices corresponds exactly to the total Betti number of the manifold.
Okay.
So, right, so in dimension 6, I mean, you have odd cohomology vanishing. You have one-dimensional H0, one-dimensional H6, and H2 and H4, they are equal dimensional by Poincare duality, right? So, so in this case, for example, the Eschenburg manifold has total Betti number 6. H2 is two-dimensional. Yeah. But I mean, already in the toric setting, you can get arbitrary high numbers. Just take blow-ups of something, then you increase the number of vertices.
Okay. Okay. Well, thank you.
Okay. Are there any other questions? If it's not the case, we can thank you. We can thank Oliver again.
Okay.
Okay.
Yeah.